Ese es. No se nos ve a nosotros apenas.
¿No?
O sea, se ven cabezas cortadas, se ve a Eloy y...
Un moment, sisplau.
Espera un momento.
Se va a oír un poco mal entonces, perdón. Haureu de parlar una mica centrat, si no sou... Good morning and welcome to our presentation. Today's presentation will be a little bit longer. We have 47 slides to be presented today, so if at any moment there is something that is not clear, you can stop the presentation if you want to comment it, or wait until the end because it will be very longer and we want the comments over the time exposition. So let's begin, as always, with aerodynamics. The last presentation we said that the tail stabilizers were in progress. We were defining the critical scenarios and that's the final result. After several iterations, we have come to the conclusion that the surfaces were need to be expanded to have a better maneuverability and of course a better stability. These tables are extracted from our provisional technical sheets, and together with the stabilizers were defined the rudder and the elevator. From boost surfaces, we have to explain that we have choose a configuration based on a half short limitation. This gives a bigger surface and that is translated to a better maneuverability and a better response to the stick control. Both deflections are big enough to provide a progressive control based on the stick deflection. For the elevator, we have choose a positive and negative similar value, exactly 20.27 degrees, and minus and plus 30 degrees for the rudder. The ailerons were defined using a flap simplification, more or less the similar method that was used in the rudder and elevator, and the deflection is similar and equal to the rudder. The fuselage was designed based on a series of elliptical cross sections. This is optimum from the aerodynamic point of view and was tested after several iterations using a CFD model built on Autodesk flow design. Using all these cross sections, this final solution was obtained. If we go to the validation of the design, we see that a drag coefficient of about 19 was obtained, which is more or less an optimum value after all the iterations that we have done. The main landing gear is an element that is always present in the flight experience. Because of the complexity of our retractile system, we have concluded that it's better for the weight impact and the cost impact to have a landing gear that is always fixed in the structural position. That is the configuration that we see in the picture. This causes that a lot of drag is generated in this zone. So a fighting is optimal for that kind of drag reduction. The fading was based on an ACA 30 airfoil. It's not the most optimum airfoil, but it has a bigger camber. That is optimum from the perspective that the shore can be reduced and the landing gear can be contained easily without the problem of having contacts against the ground level. Also, we have corrected this part just for this reason, to avoid the contact between the fairing and the ground during a regular landing operation. As we can see, using the simulation model, the drag has been drastically reduced. Here we have a 59 value and here a 44 after the fairing implementation. The propeller interference is just a first approximation of the real impact that the propeller will have over the airplane. That's something that will be seen in posterior parts of this project. So this is just a brief view of what would happen. We have used a momentum theory, which is an approximation used in helicopters and vehicles of that kind, more or less vehicles that has a rotation part that is creating the thrust. Using this, this model, we have concluded that the propeller creates more or less a coil that is around the fuselage part, which is not a critical or a significant part of the aerodynamics of the airplane. So no further iterations, no modifications over the general design of the airplane is required in that part of the project. Let's go with avionics. We have ended with the cabin design. As we have seen, as we said in last presentation, the seat was defined and some other elements. We will now talk about the cockpit. This is the frontal panel. We have used the norms to adjust the spacing and the configuration layout, and we have added our additional instruments in order to fulfill the norms and the rules that was imposed by the aeronautical authorities. This is a render that presents this layout in a more visual, more appealing way. Also, together with the frontal panel, a lateral panel will be installed in the left side of the pilot. These three controls provide the thrust, RPM, and mixture controls, which is crucial for a correct maneuverability and operation of the airplane. So it will be near the pilot and it will be easier to access these controls. The seat has been correct according to the customer's specifications. The back seat have been inclined backwards, so it will be more comfortable and it will provide more room for a parachute in the back. Also, the horizontal support have been elevated upwards, providing even a more comfortable solution. The pedals are a balance between the blockage of the feet and the possibility of a rapid and fast evacuation from the vehicle. Basically what we have done, and it's not clear because of the projector quality, but here there are atoms, some parts of metal, that are a little bit up, a little bit higher than the rest of the pedal. This causes that when the foot is trying to go out of the pedal, it's blocked. This is optimal because during a G-force of about 2 or something like that, the leg will try to get out of the pedal. So by blocking this movement, the pilot will always have the feet touching the pedals and no control will be lost. On the other, from the other side or from the other perspective, a Velcro has been omitted, has been discarded because it will impede a faster evacuation. It's a solution that is in some airplanes, but it's not recommended because of this reason. The pilot will need to detach the Velcro and it will result in a more catastrophic possibility of evacuation. The canopy has also been specified, has also been defined using the fuselage that we have seen before. This is the cover glass that will be made with plexiglass, and we have also, using literature reference, defined the point of optimum head position for the pilot. The norms doesn't say anything about this point, but we will use it because it seems that that provides a good solution and a good visibility of all the surroundings of the airplane. This is the literature reference that we have been used together with our anatomic dummy. And after locating all the elements inside our 3D model, we have seen that no interference between elements is notorious, so there is no problem with the layout that we have design. And that's something that we will see later. We have put a camera in a digital environment, and it is expected to have a free movement so the customer or any kind of people can see all the layout and the interior of the cabin in real time using a Unity-based program. Now let's go with safety systems. By norm, it's imposed that all the cabins needs to have a fire extinguisher, a hand fire extinguisher. We will locate ours inside the cabin. It's a very compact size fire extinguisher with a 10 seconds load, which is sufficient for a cabin of these dimensions, and it will help the pilot to have a better evacuation or even extinguish a little fire that it has been started in the cabin. Then let's go with the firewall. The firewall is on edge because it will isolate the engine. This will provide a protection of 10 minutes, about 10 minutes more or less, and it's made out of titanium. This is a work in progress and it needs the validation of the structures and propulsive department. And until now it seems to be the best solution because it has a huge weight reduction and a minor impact in the cost because it's a very thin layer of titanium. About the lightning protection system, there were two solutions that were feasible. One was lightning collectors located in critical points of the airplane, but that solution didn't provide a good protection when the airplane was, for example, doing a maneuver in an inverted position. So the second solution was used. That solution is based on the collocation of a grid layer of aluminium that is between the materials used in the skin. This is a representative of the skin of a fuselage made of fiberglass, not our case, but it's representative enough to see what we are talking about. There are several layers. The lining will strike, burn some of them, and when it touches the grid will transmit the electricity, the free energy, to a derivator that is basically it's a resistor, and this resistor will absorb that energy and be converted into heat energy, not damaging the rest of the airplane. So we have a full protection over all the skin of the body, and no critical damage will occur on vital instruments like, for example, the cockpit or the cabin. So the parachute is recommended, but it's not part of the company's responsibilities. That means that we have provided a system, a mechanism that permits the pilot to have a parachute in their back. As we have seen, we have designed the seat to have enough room to put a parachute and sit comfortably in the airplane. But the pilot can decide if it takes that advantage or not. It's recommended, yes it is, but it's not our responsibility. The canopy has been designed also to provide an unlock system that is, as we will see after this slide, easier enough to detach and permit a fast evacuation even during air operations. If anything happens, any kind of a scenario with critical consequences happens, the pilot has to activate or arm the ELT, which is the transmission system that will inform the rescue teams in case of an accident occurs. If the pilot is not able, for any kind of circumstances, of touching or arming this system, the system will activate when it will detect the impact against the ground. That's the procedure that we have set about the detachment of the canopy. The pilot will be flying, and when the critical situation occurs, we'll pull two levers, one for the correct and usual opening of the canopy, and one for the complete detachment of the canopy. While pulling both of them, if he applies an upper force, the canopy will completely detach and fall backwards or at the lateral, and then he will have free movement to jump if it's necessary, or if it's in the ground, just run away from the airplane.
Thank you, Victor. Okay, now we're going to talk about the wing design that we began the other day. That's the final configuration of the wing. We've added the rear spar, and now the wing is completed. Okay, in this part I'm going to talk about how we did the simulations, the structural static simulations. All the simulations have been done in ANSYS, and one of the problems that we faced is that all the entire structure was a composite structure. Composites, especially carbon fiber composites, are materials that are orthotropic, sorry. And that means that they have 3 planes in which have different properties. They have different Young modules and different maximum tensile strength in 3 different dimensions. And that requires a much sophisticated computing programs and much sophisticated simulators that we can't access right now because they are very expensive, that kind of software. So, as a measure of first approximation, we've done an isotropic analysis of the wing. Okay. For reasons of meshing, as we can see here, we've tried 2 different possibilities. The first of all was analyzing the wing without the skin. And that leaves us with a 5mm mesh that we consider that is a very good approximation, a very good mesh. While if we use all the wing with the skin, we'll get a 65mm mesh, which is not really optimal, but well, we've done the simulation with both of them. Okay, as I've said previously, we've used an epoxy carbon woven 230 gigapascals and prepec. That was we say a standard material from the repositories of ANSYS, and has these characteristics as we've said, in 3 dimensions, which we can see that the material is really bad at the Z direction. We have only 50 megapascals and minus 140 megapascals of tensile and compressive. Okay. Well, it's not ridiculous stress, this is deformation, but it's a mislead, sorry. Okay, here we can see the deformation for both configurations. And we can see that the maximum configurations is at the tip, and it's about 3.7 centimeters, which we consider that is a good, and we suppose that it will not cause slamming problems or aeroelastical problems. While in the configuration with the skin, the maximum deformation is of 1.6, which, well, it's a little common sense that the skin will redistribute the tensions, the stress a little. And if we see the equivalent stress von Mises, we've seen that in the first configuration the maximum stress is of 150 megapascals, while if we take into account the skin, we reach 85.4 megapascals. It's true that we don't know the direction of the stress, and as we are using a composite material, we really cannot tell if this is really breaking or not. But we can see that if we apply a security factor of 2, that those are the maximum tensile strength, they don't reach the compressive, nor the compressive or the tensile on X and Y. So, except for the Z axis, it's a good stress that we have. So, how can we tell that these don't break, that this stress is not located on the Z axis? Well, plotting a vector stress, that this is a thing that ANSYS could do, we see that most of the stress is located at the, well, it's not really, well, there's a lot of vectors and it's not really easy to look at. But most of the stress is located in the XY plane it's located in the skin plane, except for those ones that is really a problem that has ANSYS with importing from SolidWorks. ANSYS has a poor compatibility with SolidWorks and other CAD programs, and the automatic mesh creates some problems in the places where we have the ribs. That's why the ribs model conflicts. But we think that it's not really, those vectors of here is not really a real stress. It's just a product of the error in the import. So we can consider that there is no tension on the z-axis. So, as we said before, the stresses are good and the wing doesn't break. And here we have a map of the shear stress, the maximum. Here we have the maximum, and if we compare with the full qualities, full specifications of the material, that's okay too.
About the structure of the tail, it is designed in a similar way to the wing structure. Here we have the horizontal stabilizer. It is composed mainly by a set of ribs, a leading edge spar and a rear spar. That leading edge spar doesn't span along all the length of the stabilizer. Here in this empty space, there will be located the control system of the elevator. And well, as we will see later, that this leading edge spar doesn't arrive to the tip of the stabilizer, doesn't compromise the structure, because well, the lift the tail has to withstand is very low compared to the one of the wing, and also the higher bending stresses are located at the root. So the part of the tip is missing, it doesn't compromise the structure at all. Also, this cross-section of these spars are eye cross-sections. It can be optimized, as we will see later in the ANSYS simulation. And well, this rear spar is located at the half of the chord line, which is also the hinge line. The hinges of the elevator will be located between these ribs, here, and here, I think. There were 3 hinges. Well, the vertical stabilizer is designed in a similar way to the horizontal stabilizer. It has a leading edge spar that runs along the quarter of chord line, and also a rear spar that runs along the half of the chord line, which is also the hinge line. There will be 3 hinges for the rudder located between the ribs too.
Okay, as we have done with the wing, we proceed to do an analysis of the tail, although we do not expect any real problem because of the low lift provided by the surface control comparing to the wing. As we can see, we've accomplished a better mesh with the horizontal stabilizer than with the vertical. We believe that it's for importation problems. And for the horizontal stabilizer results, here it can seem a little catastrophic, but it really is not, because if we look at the values, the maximum deformation is of 0.62 millimeters. So we can say that it really it's not, well, it is a much worse deal than it is. And for the stresses, we can see that the maximum stress that it's applied is of 6 megapascals, that we say. If we're using the same material as before, it won't be any problem as we expected. And for the vertical stabilizer results, it's even a lower stress. The maximum deformation is only, well, I've said to 0, but it really is 4.7 per 10 minus 7. So it's nearly 0, we can consider. And the maximum stress is 0.016 megapascal. So no structural problems in this part.
That's why I said it can be optimized. still. And also I didn't comment before that the internal structure of the rudder and the elevator is composed mainly by a set of ribs that are prolongations of their corresponding stabilizer, and a main spar that will consist in a tube of carbon fiber composite. And so, well, about the fuselage structure, the fuselage structure will be a monocoque structure, which means that the skin will be a part of the primary structure and will withstand some loads. And the internal structure will be a Warren truss type. We also considered a Pratt truss type, and we compared both models. But the Pratt is designed to work better when the vertical loadings are in one direction. And considering we have an aircraft that will constantly be flying upwards and downwards, we have concluded that maybe the Warren truss type will be more efficient. Well, this truss structure will be composed of 4 longerons that run along the length of the aircraft and are interconnected with carbon fiber rods that will act as the vertical, diagonal, and horizontal members of the truss. And they will be joined by rivets and maybe with e-glass and epoxy gaskets to join this truss. Also, these longerons, they may have a core of polyurethane foam to make some sort of sandwich structure in these longerons in order to make them withstand more loads with little weight addition.
Now we're going to talk about propulsion system. Remember that we select the engine, so now we are in provision to select other elements. Let's begin with the variable pitch propeller. I just want to remark the most important parameters of this system. It is a variable pitch because we want to modify the pitch angle so the propeller can absorb all the power that is provided by the engine. Then it is one line here. It means that it's the basic type. We have chosen this type because it adapts to our engine. Then there is 125. It means also that it's the basic type, and it has good aerodynamic performance for our purposes, so we have chosen that. Then there is three blades, and then we have installed some counterweights because if the governor fails, this helps us to get again the low pitch so that the aircraft could be again controlled. We have a scheme here of the hub. It is composed by the spinner, which is made from an aluminium alloy. Then here there is the display. We will mount the blades, and there is the governor. In the other picture, the other drawing, we can see a detailed drawing of the governor. Just say that it's an hydraulic governor, sorry. And remember that his purpose is to modify its angles. Well, let's move now into the inverted oil system. His purpose is to lubricate the engine, and well, we have to. This system allows the pumps to pump all the oil in between the oil sump into the engine between flexible hoses in each attitude of the flight of the airplane. But this oil that is used for lubricating the engine has to be cooled. So what we have done is to install an oil cooler. It is based on 2 oil coolers which are mounted into the rear part of the engine and in the front part. And then also we have installed another systems which are the induction system and the exhaust system. What they do is to take the, well, in this case, they take the air from the atmosphere and they bring it to the engine through the pipes, and the exhaust system takes the fumes and the gases from the engine and they bring it to the atmosphere by using the pipes, which are made from stainless steel to avoid corrosion.
Well, on the financial department, we finished it and extract the conclusion of the market study, and we started and we see that as we work on the market study, we can extract the basic aspects of the feasibility study. Well, on the general conclusion of the market study is that the unlimited market is really reduced. As we can see in the previous, the previous explanation on 3 weeks ago, we see that only 50 pilots compete on the World Aerobatic Championships. That means that the market is really reduced, so if we are going to sell only aerobatic aircraft to the limited market, the company on a long term will be unviable. So we have to look for another sources of income in order to have stability over the years. Then, the second basic conclusion is that we are producing a new aircraft and we're expecting the other pilots to change from their aircraft to ours. That means that our aircraft must be really easy to use and very comfortable for the pilot. The third important conclusion is that as we see, the limited market is really close. So we need to see for other in long term. We need to look for other markets. We analyze the other aerobatic competitions, and we see that intermediate and advanced market could have a gap to where Feiheit ALPHA must be introduced. And the fourth important conclusion was that to sell our aircraft, we have to have advantage over our rivals. That advantage should be in aerodynamics and performance. Having aerodynamics and performance advantage over them will be for us a marketing thing that we can use to sell our aircraft to the pilots. And finally, we have to add that having a best performance doesn't imply that we succeed on the market. This conclusion is extracted from the Thico H540 aircraft. This aircraft has the lowest weight of the market, but it's not well implemented. It's not absolutely. It doesn't dominate the limited aerobatic market. Well, first, analyzing all the aircraft, we can understand that our gap in the market will be more or less this one. As we see on the first presentation, the gap was actually including this part, but we have to say that the gap will not fulfill this part. Why? Because as we see, we decide that the price must be between 300,000 years and 100,000 euros. That price is as we see, is an expensive price, but it's according to the other competitors. Why we have choose this price? Because this is a high price that will protect the value of our aircraft. We are manufacturing a high performance aerobatic aircraft, so we have to show this high technological this high technological with the price of the aircraft. But we didn't have to surpass this value, because if we surpass this value, that means that we have an economic disadvantage over the extra aircraft. So between these values, we can conclude that we have some advantage in one rivals and disadvantage in other rivals. However, this disadvantage will be covered by the best performance of the aircraft. Well, as you can see, for example, Sukhoi is more or less in this way. They may have a lower price of sale, but we will have better weight performance. Then this price will have an advantage over extra and less. Well, as we see on the international market, we have this distribution on the major countries that contribute on the aerobatic market. As we see, the leading ones are basically France, Russia, and United States. Well, as we analyze, this market share is extracted from the 4 years of World Aerobatic Championship. It's need to analyze the 4 years because in 1 year, as there are not many pilots competing, there can be singularities in 1 year. So the values of the market share cannot be really precise if we only analyze a few years. So these are the results that we extract. So as you can see, in short, well, from our conclusion, in short term, our company will be established in Spain. So our first market will be Spain, because basically for proximity and nationality. That means that we can use the nationality arguments to combine the pilots from Spain to use our aircraft. Analyzing the Spanish market, we have basically only 3 pilots: Castro Fontoa, Juan Velarde, and Anselmo Gano. These 3 pilots participate in unlimited aerobatic championships more or less every year, and they are not at the top of the competitors one, but they have quite good results. We have to say that Juan Velarde also participates in the Red Bull Air race, so their name amongst all the pilots is quite well known, and they are well established inside the pilot's world. Well, in medium term targets, that means after introducing and trying to convince the Spanish pilot to use our aircraft, we are going to France, USA, Germany, Great Britain, Czech Republic, and Switzerland. And then on long-term target, Russia, because as we said on last presentation, most aerobatic pilots use Sukhoi aircraft, which are Russian, and that means that the market is really close. Then, apart from the nationality and the place that we are going to look for, we make a market study of the aerobatic aircraft companies. As you can establish, there are basically 6 competing, and the ones who absolutely dominate is Extra Aircraft. This has a market share of 35%. However, we have to say that in 2005 the market share was about 50%. So the implementation is really high. We extract from the data that we obtain that basically their success is thanks to their expertise and their background. They are producing aerobatic aircraft since 1988. That means they have a really important background. The company was designed by a pilot. That means that the interference between pilots and designers are really close, so they know exactly what they are producing, and that the pilots will be very good at receiving their products. Then, from these companies, we split the ones who only produce aerobatic aircraft and the ones that produce aerobatic aircraft and other kind of aircraft. Basically, 3 companies produce aerobatic aircraft only. XMR, which produces 2 kinds of aircraft, XA41 and XA42, the one-seater version and the 2-seater version. Extra Aircraft, as we said, they have a more variety of models. And finally, the MX Aircraft, which is the same as XMR. So from these 3 companies, we analyze basically XMR. Why? Because as we analyze them, we see that they were founded in 2004, but in 2005, and in 2014 they have financial issues. So we see that, focusing on these companies, we know what we don't have to do in order to be viable over the years. That means that we have to surpass the market share in order to know that we really are a good company and we are going to be well implemented on the market. This 10%, as you can see, is 8.73%, is quite strange because although perhaps it seems that it's not a less market share, it's important to say that this was not obtained and get it with all the XA41 aircraft. This market share includes aerobatic aircraft that were produced for a similar country, for the same country, but Asian aircraft. So basically, the 2 aircraft that they are producing didn't obtain enough market share, so they become inviable. The other 2 extra aircraft and MX aircraft are viable, and we extract that their success on the market is because they produce new aircraft, but the veteran pilots receive them quite well. they use them, they are comfortable, and they operate really well with them. So they made they have the stability that the MX aircraft didn't have. Well, from this aircraft you can see that although Fitco Aeronautics looks like really little market share, we have to say that it also produces other kinds of aircraft, but they have a contract with Red Bull Airways. Actually, they have 12 planes competing on Red Bull Airways. So apart from the World Aerobatic Champions, we have other sources of income which are there with Red Bull Airways. Well, finally, as we analyze all the things, we make a diagram when a SWOT analysis to know what are our strengths, weaknesses, opportunities, and threats. Basically, our strengths was the performance aerobatic theaters. We are expecting to have a better performance, not very huge, but a bit more. We have a small advantage over our competitors about the performance and aeromatics features. I usually use some comfort of the pilot, having a low weight over some of the rivals, have a balanced airplanes. As I said, it's not that we have some good quality that we can sell to them. It's all the aircraft which is well balanced, has some little advantages over all the aircraft. We have the latest in material selection. We have some economic price advantage over the main rival, which is extra. And the product is absolutely designed by aeronautics experts. That means that the quality behind the product is basically certified. And another thing is that we are selling the airplane as a usable marketing product. That's what we introduced in the last presentation, that although we are selling our aircraft to pilots, we are also selling the aircraft as a marketing thing. That will allow us to have two sources of income. One, the sales to a pilot, and then the use of the aerobatic aircraft sells to a company that will use the aircraft for advertising themselves. Or not just selling the aircraft, but using our aircraft that we have and sell them and they can use our aircraft to promote themselves, not buying but using it. For example, if they are going to make an advertisement on TV, they can use our aircraft. We can give them, we can sell them for a period of time, and they can use it, and we can get another source of income that is not exclusively from the sales. Our weaknesses basically are: we have no expertise with the pilot. We are producing a new model. We are aeronautics. We are not pilots. So the part that we don't have the experience that the pilot provides to our aircraft. So some aspects we are very more weak than the other companies. Well, we have to say that we are in fact expecting to have an interview with a pilot, but it's in the air. Then we have another remarkable advantage over the rivals in terms of performance and aerodynamics. Having something really best from the other ones, it's a really attractive thing, but we don't have that thing. We have to know that we don't have that something that is much better than the other ones. We have exclusively manufactured one model. That means if something affects that model, we are basically out of business. And we have half important of itself, few sales are expected over the year. That means as we see, the limited market is really close, so each sale that we make is important. Because we are not expecting to sell 30 airplanes a year, because there is no market. So each sale that we make is really, really important. Then we have opportunities. We see that we have a cap on the weight price ratio, and we are clearly identify the targets, the pilots and the companies that can use our aircraft to advertise themselves. Then we have the internationality of the market. We are selling all around the world, and that means that in some countries, for example, France has an economic crisis. This should not affect our sales because we are spreading around the world. And finally, that there are potential pilots on the national market, that we see there are 3 basic pilots. Then we have 2 sources of income, one sales from the pilots and sales from the marketing. And marketing, there we have marketing possibilities for increasing and generating reputation. For a company, for the population, if they see a company using an aerobatic aircraft and start doing barrel rolls, backflips and something like that, it's really attractive for the population, and the population will remind this company with the aircraft. That means that it's a good marketing product. Well, as you see, the high visual impact of limited aerobatic maneuvers over the population, and the high amount of national and international events in the sector. This aspect is really important because that means that the companies know that there are many places that they can advertise using our aircraft. I mean, in Barcelona they make the Feiheit ALPHA, and any pilot can go and participate there to advertise a company. The similar event is done in Dubai. So there are many kinds of these events that the companies can use to advertise themselves, focusing on not the sales to the pilot, but on the sales of marketing. And finally, the threats. We have to say that the smallness of the limited market. We have to be conscious of that because we are in a very small market, and we have to know to look for other sources of income and know that if we are focused on the limited market, at the end we will be blocked. And finally, another important threat is that any accident affecting Feiheit ALPHA or any aerobatic aircraft will be affect the market image and will affect directly to our sales. Finally, bad results on the championship competitions will affect us a lot. Why? Because as we expect, if we can convince a pilot that participation in the World Aerobatic Championship with our aircraft and is able to perform a really good competition and reach at least at the top 10, that means that many other aerobatic pilots will be easily to get combines to use our aircraft. But if they don't get good results, it's impossible for them to use our aircraft. And this is the general another threat is the general known of the aerobatic and unlimited market by the population. That means basically that anywhere you can go, you can for a kid or to any person, you can not expect them to know about the unlimited market because they see aerobatic aircraft and they say, I don't do something, but they don't really know what it exactly means. We have also taken into consideration that the competitors will make improvement on their aircraft, that at first, perhaps because we sell them on one time and it's new, it's the best technological aircraft on the market, but as the years go on, the competitors will start to improve their aircraft or keep improving their aircraft. Another thing is that the unknown of the marketing potential for aerobatic airplanes. The companies doesn't know that, it's not well implemented to use aerobatic aircraft for advertising. It's in some punctual places or events, yes, but not widely spread. And finally, the dependence on the pilot skill. Obviously, this is really related to the result of the championship competitions. And then we have more or less the idea of what the poster is here. Well, that's the end of the presentation. We have any questions?
Molt bé, que